So for now we will focus only in Python, and I will show you 3 different libraries that we developed in order to show you the potentiality of this service. So let's start with 2 libraries, CandLib and CDLib, that for which I am the main maintainer, that are libraries that allow you to work with complex networks. In particular, CandLib, which is the first that we will discuss, is a library dedicated to simulation of epidemic spreading on top of networks. So CandLib stands for Network Dynamics Library. Is a library that allows to use directly several compartmental models, the classical SI, SIS, or SIR that we will see in a few minutes as an example, to simulate how a virus spreads all over a network. And also, we have a lot of variation of the models. We have the chance to not only simulate spreading of epidemics, but also of opinion dynamics. So we have 2 families of different processes that can be simulated with a common grammar, with a common library. And moreover, the library also allows you to define new models from scratch and to simulate on real data. So the first thing to do here is to import the library and then generate a graph or a load from real data. Now, since we are working with network X as a background, the library works both with network X and as well as with iGraph. We can just generate a synthetic network like the red or shiny one with 1000 nodes. Okay, it's enough for our testing for now. Once we have generated this network, what we can do is to select a model. In particular, we will select the SI model for this first simulation. SI model is a model in which each node is either susceptible or infected with a given probability, with parameterized by beta. It will be a transition from one status to another at each iteration. So we can see that the model has 2 different statuses. We can configure the probability of transition and the ratio of initial infected nodes. Then we can execute the model and visualize the trends for susceptible and infected nodes through time. So we will see how the susceptible node decreases as time goes by at the increase of the infected one. And then we can also visualize, for instance, for each iteration, which is the absolute value of users that switch status from susceptible to infected. This is a very silly example, a very simple model that can be extended. For instance, we can propose an SIS in which we have another parameter that is the probability for an infected node to become susceptible again. So you can see that the procedure is the same. You can instantiate the model, configure the model, iterate, make the simulation, and then visualize the trends and the prevalence plot. So easy peasy. After that, just to provide another example, we can move to a more complex model, which is the SIR, in which instead of having a transition from infected to susceptible, we will have the probability that an infected node became recovered, meaning that to some extent it develops some kind of resistance to the virus, okay? And so it cannot be infected again. So we have another statuses coded by R removed, and we can parameterize it by gamma, probability that an infected node will become removed. So we execute our simulation, and we can see that we will have this time 3 trends, because we have 3 statuses, one for the susceptible that decrease, one for the removed that increase, and one for the infected nodes that reaches at a certain point a peak and then decrease because infected will become time after time removed. And this, the same can be observed by the diffusion prevalence plot. Here you can see a few models that we have already implemented that are only for the epidemic part, and they are not all the one available, and also we have also models for the opinion dynamics side. So this was the first library. Let's move to another library still dedicated to network analysis. In particular, I would like to talk to you about CDLib. CDLib is a network that is a library that is dedicated exclusively to community discovery, so clustering on top of network realities. As all the libraries that we developed and I will show you today, or even this library is for this library is available a documentation online. So if you click here, for instance, you will get prompt to this website on Read the Docs, in which you can have all the documentation on the library, on all its methods, and so on and so forth. CDLib particularly is interesting because so far is the widest library in terms of algorithm offered for community discovery independently from the language. CDLib offers up to 80 different algorithms to cluster network entities, and most importantly, it allows both static clustering and dynamic clustering. So it's one of the few libraries that allow to do so. However, one thing to notice that CDLib and DLib, scikit-mob, and all the other libraries that we develop not only have freely available, accessible documentation or read the docs, but they also have the ability to look in the source code on GitHub usually, and a source code that is open to pull requests, to bug fix, and to the integration from third party. So if you have any algorithm, if you have ideas, if you found some bug, please let us know. So coming back to our tutorial, even here what we have to do is just to import the library, and then we have to generate a network. In this case, I would like to use this network that is built upon the interaction among the characters of a well-known TV series, which is Game of Thrones. So we will consider the first season of Game of Thrones, and we have individuals that are represented by nodes in the network, and the edge will represent individuals, characters that are that appear together in a single, at least in a scene during this season. Okay. So we can read the data. This is the path within my workspace, and then we can select the clustering algorithm to apply. In particular, here we will test label propagation and laden. Then the library allows us to compute on the clustering some information, for instance, the name of the algorithm used to compute the clustering, the parameter of the clustering to keep track of different instantiation of the same algorithm on the same data. We will be able to observe the community obtained as a list of lists. So for instance, here we will have the first community composed by these nodes, the second community composed by this other, and so on and so forth. And then we will get also information regarding the kind of the partition, either for instance it is an overlapping or not, meaning that a node could belong or not to more than one community. We will get information regarding the coverage, so the fraction of the nodes that are correctly assigned to at least a community, and then other information like the computation of a JSON format to store on file the result obtained. Moreover, the nice thing of this library is that it exposes not only more than 80 different algorithms to compute clustering, but also more than 30 functions to evaluate the goodness of the clustering. So for instance, you can compute the average internal degree for the obtained partition. This is a summary looking at the average, the standard deviation, the mean and the max, or even still the average internal degree for each individual cluster. This could be done, for instance, computing the modularity, the conductance, a lot of different quality function. And then other thing that we can do is to compare two different clustering of the same network. For instance, if we have a laden clustering, if we have a label propagation clustering, we can measure how similar or dissimilar they are by means of normalized information or other measurements. And most importantly, we can also visualize clusters. So for instance, let's assume that we have this network here that is the Game of Thrones network. Here we can visualize the clustering by different colors. So we have green nodes that are in the same community, red identifying other communities, and so on and so forth. And we can visualize this for all the clustering that we have computed. Of course, this could be an issue when the network is big. And so CDLib allows also to visualize this more compact visualization in which each community is just collapsed in a single node, and we can see the relation among different communities in a graph. So here we have the blue community, that is this one, that is clustered, that is visualized as a single node, and here they are the relation with the other community identified. Most importantly, CDLibs come also with a several visualization, automatic visualization to explore the data. and in particular to explore, for instance, the distribution of fitness function. For instance, here, the distribution for the two clustering that we have computed, laid and label propagation of the internal edge density, or even to compare on a scatter plot the different I don't know, community sites and internal edge density or other measure that we have among the fitness score for different clustering. So for instance, here we have this Cartesian plot bar, Cartesian plane, in which dot in orange represent label propagation community, as in blue leading ones, and we can see how each community behave in terms of sites with respect to the internal edge density. So we can see, for instance, that we have the biggest community for label propagation, that is the one having the lowest edge degree density. So this is a qualitative analysis that is very nice to do. Moreover, we can also define similarity or purity with respect to ground truth. For instance, we can say that the families in the show represent the ground truth community. So we can see how much the identified community resemble this original partition, and we get some information regarding that. And we can visualize several information also regarding the similarity of partition on synthetic ground truth, like the one generated by the classical FR benchmark. So as you can see here, we have computed 1, 2, 3, 4 different clustering approaches on a same network, and we got this confusion matrix that show us how similar are partition by partition the different algorithms applied to a given network. So as you can see, CDLib as well as NDLib is a complete library that spans from data loading, model application, evaluation, and visualization of the results. More or less all the libraries that we are developing in all the fields have all these different steps. So just to switch focus now, let's move to this third library that I would like to talk to you about. It's a library that goes a little bit outside my area of expertise. I am a network scientist by background in computer science, and this works of Luca Paparardo and colleagues that basically developed this scikit mobility library, skmob, that provides an access like the classical scikit-learn framework. So they have this fit and transform, fit and apply, fit and predict taxonomy of the library that is designed to handle mobility data. So the library, as first step, needs to be imported, and here we will see how to apply it to do very basic stuff to do two different real world datasets. The first one is BrightKite, which was actually, because now it does not exist anymore, a location-based social networking, for which we have this very nice dataset available online. And here has been shown how skmob, after downloading the data, is able to transform it and store it in a trajectory data frame. Trajectory data frame is an extension over the classical pandas data frame, allowing to store specific structured data like trajectories. And you can see here, for instance, an example in which you have the date time, latitude, longitude, and location ID for the specific point. Then skmob, scikit mobility, allow also to filter the users, filter the points, and visualize them. So for instance, here by accessing properties of the trajectory data frame, it is possible to take the point of a single user, to sample for this user 200 points, for instance, to plot the stops of the users, and then to plot the trajectory, the overall trajectory. As you can see, this will be the result, where the green square are the stops, and the edges here represents the trajectory, and so on and so forth. Let's move to a little bit more complete, complex dataset, the GeoLife one. GeoLife dataset is collected in Microsoft Research Asia and has basically the mobility tracks for 182 individuals from April 2007 to August 2012. So there are plenty of trajectories, as you can see, a lot of kilometers that have been percursed by the users, and a very long duration in terms of travels. So the first thing to do is to load the data here from the local data geolife sample txt.gz, that is here in our folder, and sort the data by date time in order to better build the trajectory. So doing so, we will have at the end this trajectory data frame, for which we will see a head in a while, that represent all the trajectory of a given subset of the users. Okay, so latitude, longitude, date time, AUID, user ID. Then, as before, we can just plot the trajectory of a given set of users. As you can see, these are users in Beijing. You have some stop, you have some routes, and so on and so forth. And then we can ask how many users are in this sample dataset, how many points we have, what is the time windows of observation, and other very simple questions. And you can ask this question very easily by interrogating the trajectory data frame. So you will see that you have 2 users in this sample that generated 270,000 points for time windows of more than 146 days. So let's say that we would like to focus only on a first user, so we can select it, and we will get this data frame that is filtered for a single user, and then we can visualize its trajectory on the map. Let's see, these are the trajectory only for the user with ID number 1. Okay, it's easy, nothing particularly complex to achieve. Then we can preprocess the mobility data. For instance, we can filter them, compress them, identify stops that are important to identify travel, and so on and so forth. So let's start with filtering trajectories. Let's assume that you have this user or a set of users, and that you would like to identify only those points, only those trajectory that have a maximum speed of 500 kilometers per hour. Okay, so you can do something like that using a filter, and then you can also visualize the parameters of the filtered points. So you can see that you have filtered by this velocity, you have decided to not include self loops, and so on and so forth. Okay, and finally you can visualize how many data points in the trajectory, in the filtered trajectory, and the filtered points, so you can see what remains from your filtering procedure. Then you can also compress trajectory. This is quite useful in order to reduce the number of points that are used to represent a trajectory while preserving its overall structure. So this is done to simplify the data while maintaining high the quality of the data itself. Okay, and to do so, one way could be, for instance, to merge all together in a single point, so all those points that have a spatial radius of a given distance. So in this case, all those points that fall in a spatial radius of 0.2 kilometers from each other will become a single point. So we can use the compression library and then run everything, check what are the parameters of the transformation here, just to have all the history of the transformation. So you have the filtering, you have the compression, and so on and so forth. So as you can see, this is an extension of what we had before. So we are keeping track of all the transformation. This is a very nice thing in order to document our transformation with the data. And then, as before, we can understand how many points we have loose, how many we have aggregated, and so on and so forth. And finally, we can also make a stop detection. A stop detection is important because it allows us to identify those locations where the user spent at least a given amount of time. So here, minutes for a stop is the keyword, or and also can specify the distance to identify the set of points representing the stop. Okay. So this works this way. You can do the detection phase. You specify the radius factor, the minutes for a stop, the spatial radius, and so on and so forth. All the information that can you find completely in the documentation. You get this new data frame, and also, as before, you can keep track of the transformation looking at the parameters. So you will have the filter, you have the reading from file, the filtering, the compression, and the stop detection. As you can see, you keep track of everything. And finally, you can visualize the identified stops that are represented here as this square here in the map. Okay. After that, what you can do is to transform this stop in trajectories. Okay, so you can basically do a few preprocessing steps and then plot the stop maps as before, but looking this time at the specific users and where the stops are within its thresholds. Okay, so you can see that we have both the trajectory and the stops identified by the algorithm. Starting from that result, you can also identify trips. Trips basically are trajectory that start and end from two consecutive stops. So here we have the add, here we can give it a filter, and then we can identify, for instance, starting from two different stops, the trajectory goes from one to the other. Okay, quite easy, right? Of course, all the maps are resizable, downloadable, and so on and so forth. And finally, one thing that can be done is to compute the length of the trip and the distance between origin and destination, for instance, for this trip. That is quite easy to do it. Okay. Okay, these for sure are just very simple example of what can be done with these three libraries that are vastly more complex of what I show you today. The main thing to remember is that they are not the only three libraries that we are shipping within the SoBigData method development method development facility. So you have several libraries, several more will be added in the future. And most importantly, remember that you can work on your own data. All the instances are local instances, so basically you have your own dedicated virtual environment virtual machine when you execute your code. And most importantly, at the end of this, you can also, even if you are not seeing this in this presentation, we can also select among different sizes for the number of cores or resources or RAM, for instance, for the machine you would like to use for your experiment. So if you have any questions, you can contact me by email. You will find the information